Welcome back to The Explainer. Today, we're putting on our senior systems architect hats, operating as forensic chemical engineers. Our objective? To reverse engineer unknown chemical binaries straight back into readable source code. Now, if you've got a background in software engineering or math, you are absolutely going to love the logic we're using today. We're going fundamentally backwards. We are taking the raw compiled output data from the lab and extracting the precise atomic syntax that actually built it. It's all about translating pure, chaotic chemical noise into elegant mathematical order. So let's dive right in. Here's our execution plan. We're going to run through the reverse engineering mission, parsing the metadata, the decompression algorithm, data validation and rounding, scaling to production build, and finally, final system syntax. Let's get to it. Starting with Section 1, the reverse engineering mission, where we decode the binary. To effectively decode these chemical binaries, we really need to contrast two core concepts. Think of the empirical formula as our highly compressed, minified code. In nature, chemical processes optimize for efficiency, giving us the simplest operational whole number ratio of atoms. It's functional and mathematically sound, but it's totally stripped down to its barest logic. And you know you can't execute a complex program on just minified logic alone. The molecular formula, on the other hand, well, that represents our full production build. This is the exact sequence, the absolute number of atoms existing in a single, functioning molecule out there in the real world. Our mission today is to start from scratch with raw data, find that minified code first, and then scale it all the way back up to the complex production build. Moving on to Section 2, parsing the metadata, percent composition. Okay. Taking a look at the system architecture diagram we've got here, you can clearly see our exact logic path. We initialize our reverse engineering algorithm by parsing the percent composition. You can basically think of this percent composition as the elemental metadata of our sample, literally the percentage by mass of each element present. But, percentages are just raw data bytes. To make them readable strings, we have to map a route. We start from the raw mass of elements, divide that by the molar mass to get our moles, which is standardizing our data blocks essentially, and then divide those by the lowest number to get a baseline mole ratio. Finally, we convert that ratio to the lowest whole numbers, and boom, that final clean output, that's our decompressed empirical formula. Which brings us to Section 3, the decompression algorithm, 4-step execution. As systems architects, you must execute these instructions strictly to avoid syntax errors. Let's walk through the exact standard operating procedure. First, assume a 100-gram sample. Now, this step might sound like a bit of a hack, but it's incredibly elegant. If you're given percent composition, this simple assumption instantly converts your percentages directly into manageable grams without altering the ratio at all. Subsequently, calculate the moles for each element using its standard molar mass from the periodic table, transforming weight into actual atomic counts. Concurrently, divide all resulting molar values by the smallest value in the set. This standardizes the data and gives us our baseline ratio to work from. Finally, format to the nearest whole number ratio. This locks in your syntax and yields the empirical formula. Let's hit Section 4, data validation and rounding, ensuring integer integrity. Right here, we absolutely must pause the algorithm to run crucial data validation. Let me enforce this with a direct command. Ensure all ratios are integers. In chemical formulas, absolute integer integrity is completely non-negotiable. Think about it. You literally cannot have half an atom in your source code. Half an atom is going to crash the chemical compiler entirely. So evaluate all calculated molar ratios. If you run your algorithm and identify a non-integer decimal output, like a 1.5 or a 1.33, you cannot simply round down. Rounding down drops vital data packets and causes a catastrophic failure in the compound structure. Instead, you must apply a multiplication factor to the entire set to clear that decimal. For example, if your output is 1.5, you must apply a multiplication factor of 2 across the board to yield a clean, perfectly stable integer of 3. Let's look at hematite for a second, the iron ore sample you're seeing right here. This is a perfect case study. When we run our decompilation algorithm on its raw mass metadata, it initially outputs an iron to oxygen ratio of 1 to 1.5. Because that 1.5 breaks our integer integrity rule, it triggers a validation error that forces us to multiply the entire ratio by 2. This brings us to exactly 2 iron atoms and 3 oxygen atoms. By doing this, we successfully reached the validated crash-free integer syntax of Fe2O3. All right, Section 5, scaling to production builds, the molecular formula. So, With a validated, error-free empirical formula securely in hand, we shift our focus to scaling our beta version up to the full source code, the molecular formula. To scale up, we have to find our exact integer scaling factor, which we refer to as the multiplier n. To do this, compare the compiled mass of the empirical formula against the actual experimental mass of the production version. Divide the true molecular mass by the empirical mass to find your multiplier n, and then multiply your subscripts accordingly. Just looking at the table here, our beta version CH2O has a compiled mass of roughly 30 AMU, but our real-world production build weighs 180 AMU. Divide 180 by 30, and your multiplier n is exactly 6. Multiply your minified syntax by 6, and you deploy the full production build, C6H1206. That multiplier is literally what breathes life into the code, turning a basic ratio into a fully functional glucose molecule. Pretty cool, right? Next up, Section 6, Final System Syntax, Reading Practice. Finally, clear technical documentation requires precise verbal articulation. We need to master the verbal syntax for formulas containing parentheses. When you're reading off decompiled source code to your engineering team, precision really matters. For example, you strictly read this string as NO2 taken twice. You don't just read the letters consecutively. You have to clearly indicate the presence of the structural grouping by pausing and saying taken twice, or taken 3 times, depending entirely on that trailing subscript. Before we log off today, I want to leave you with a thought regarding the resilience of this standard operating procedure. If the initial data packet, that raw % composition metadata we start with, contains experimental anomalies or corruption, how does our rounding logic and integer validation process compensate for that noise? Think about how the algorithm forces clarity out of chaos. Keep that in mind the next time you're compiling chemical scripts. Thanks for tuning into this Explainer, Architects. Good luck with your decompilations.